Hi, topic for this session is conversions in binary number system. In the previous session, we have discussed about four number systems that are helpful in understanding the computers and its working. But eventually, computer understands one number system, that is binary number system. The four that we need to understand were decimal, binary, octal, and hexadecimal. So coming back to binary number systems and its conversions, the conversion of the binary numbers to other base numbers are as follows: binary to decimal, decimal to binary, binary to octal, octal to binary, binary to hexadecimal, and hexadecimal to binary. In this first two conversions, that is binary to decimal and vice versa, we have already covered in the previous session. In this session, we will try to cover rest four of them. For converting binary to octal and octal to binary, and binary to hexadecimal and hexadecimal to binary, there are two ways to do that. First is to convert those number systems, for instance, octal and hexadecimal to decimal first, and from decimal then to binary. And second method is converting octal and hexadecimal numbers directly to binary number system and vice versa. Right? The first part we have already covered in the previous session, in which we discussed how to convert decimal number into octal, octal into decimal, but decimal to binary and binary to decimal. So that would be an indirect way to convert binary to octal and binary to hexadecimal and vice versa. So we'll talk about the second method to do that, that is directly converting from octal or hexadecimal to binary number and vice versa in this particular session. So before we start those conversions, there are certain points that we need to keep in mind or remember while doing the conversion, or we can say these are helpful in understanding the concept of conversions in binary numbers. First is the powers of 2 should be very clear in our mind. Although we should know about powers till 2 to the power 10, but in this particular session or conversions, we require a maximum of 2 to the power 4 to understand the concept, right? So the second point is that the relationship between bit and byte. So one byte consists of 8 bits, and each bit can represent two values, 0 and 1. So eventually, if we combine all 8 bits, how many combinations are possible? That is 2 to the power 8, that is 256. This is the third point that we need to understand, right? We'll come to that after this particular concept, that is bits permutations. So we should understand the permutation that I was talking about in the previous slide also. So if we are considering one bit, there could be two possibilities, or we can represent two different items with the help of one bit. So if it's 0, we can say this is the first, I represent the first item, and second, if it's 1, we say it represents the second item. So there are two possibilities or permutations of one bit. Similarly, if we talk about 2 bits, there are 4 different possible combinations, that is 0 0 0 1 1 0 and 1 1. Talk about 3, there are 8 possible combinations starting from 0 0 0 to 1 1 1. We talk about 4, there are total 16 number of possible combinations, right? Or to represent a value from 0 to 15, we need 4 bits to represent them, right? So now how many items can be represented by one bit? That is 2. Already told you. With 2 bits we can represent 4 values. With 3 we can represent 8 values. With 4 we can represent 16, and with 5 bits we can represent 32 values. So if we combine this, understand this concept, we can take it as 2 to the power number of bits is the number of item we can represent, right? This is how it goes. Okay, now bits required to represent each digit in different number systems. In hexadecimal, how many bits do we require, or bits do we require to represent a digit in hexadecimal? There are 4, we require 4 bits. Now let's try and understand this 4-bit concept. 4-bit concept says, if I have a digit in hexadecimal, one digit in hexadecimal, and I try to convert that digit into binary, so each bit or digit in hexadecimal would have 4 bit or digits in binary, right? So for example, if I have 8 in hexadecimal, right, and want to convert this into binary. So 8 in binary will be represented with the help of 4 digits or bits, which in hexadecimal is represented by 1 digit. Right, this should be very much clear in our minds. So this is the table that represents each of those 16 values. Let's take an example of D. So D is 13 and it is represented by 1101. Right. Similarly, for octal, you require three bits or 3 digits to represent an octal digit. Right. So it again goes with the, like, there are 8 combinations of possible combinations when we use binary numbers. Sorry, 3 bits. Right. Now let's do the actual conversion. Right, we have understood the concept, all those concepts or point we have understood in the previous session. We'll implement that in the conversion. Now let's see a scenario in which we have to convert octal number into binary number. So octal number is 162. I told you each digit in octal is represented by 3 bits in binary. So 3 bits for 1, 3 bits for 6 and 3 bits for 2. So we require total 9 bits, or you can say digit, in to represent 162. So for each digit, we let's separate those digits in octal and we write 1, 6 and 2 in different brackets. So 2 has to be converted into 3 bits. So for 2 we have 0, 1, 0. For 6 we have 1, 1, 0. And for 1 is 0, 0, 1. Now we combine this and we get 0, 0, 1, 1, 1, 0, 0, 1, 0. So zeros on the left hand side doesn't carry any value, so we can remove that, and the final equivalent, binary equivalent of 162 octal is 111 0010. Right, let's convert it back from binary to octal. Right, so how many the number we are taking, like example we are taking is 111 0110. Okay, so now how many bits do we require to form 1 bit or 1 digit of octal? 3. So we'll start pairing those binary number starting from the right hand side in the combination of 3 each. So it becomes 110 as one group, and 110 as one group, and 1 as one group. So 1 is having just 1 digit. Let's put 2 zeros in front of it and we make 3 groups of 3 bits each. Right, so first 001 is 1, 110 is 6, 110 is 6. Octal equivalent of 1110 110 is 166. Okay, let's start with conversions from hexadecimal to binary. Let's take for that we are taking an example right out here. So example is 16F, which is in hexadecimal, and we do know that each digit of hexadecimal is represented by 4 bits of binary. Right, so let's separate those 3 digits in hexadecimal 1, 6 and 5F in different sections and write its binary equivalent. So binary equivalent of it is 0001 for 1, 0110 for 6 and 1111 for F. Right, so when we combine it together, it becomes 0001 011 01111, and the zeros on the left hand side doesn't carry any value. So therefore the binary equivalent of 16 hexadecimal 16F is 101 101 111. Any one number in hexadecimal is again represented by 4 bits in binary. So therefore a binary number, we group them in the combination of 4 bits each starting from the right hand side. So we group them 1. Okay, so it becomes 16D. Right, so hexadecimal equivalent of 101 101 101 is 16D.